In the last part of the lecture, we'll look at solving simultaneous equations where one of the equations is linear and the other one is quadratic. We'll look at three different cases: a linear equation and a parabola, a linear equation and a circle, and a linear equation and a rectangular hyperbola. So just to illustrate these graphically, in the first case, if we have a parabola and our straight line, the straight line could cut the parabola like this. Alternatively, it may not intercept the parabola at all, or it could just touch the parabola at a single point somewhere. In the second case, we'll consider a line and a circle. As before, there are three distinct possibilities. The line might not intercept the circle. It could cut through the circle in two places, or it might just touch the circle at one point. In the last case, the rectangular hyperbola and the straight line, the rectangular hyperbola has a shape something like this, in two quadrants, and you should be able to see that we'll have, as before, three possibilities. The line could intercept in two places, it could just touch the curve at one point, or alternatively, it may not intercept at all. We can't solve this type of simultaneous equation where one is linear and one is quadratic by elimination. That won't work. So we have to adopt a different solution strategy, and we'll solve them by substitution. We begin by making x or y the subject of the linear equation, and then substitute for x or y in the quadratic to get an equation in one variable. Now, often one variable is easier to substitute in the sense that it will give an easier equation to solve and will result in less manipulation than the other. And with a bit of experience, you'll learn quite quickly which variable is going to be the best one to substitute into the quadratic. You then solve the quadratic to get the solutions. There could be real and distinct, two values. There could be real and equal solutions, or one value, or there may not be any solution. Once you've done that, the solution, if it exists, can be substituted into the linear equation to find the value or values of the other variable. Let's consider case 1, the parabola. We want to find any points of intersection of the following graphs: y equals x squared minus 4x plus 5 and y equals 2x minus 4. Write it as 2x minus 4 is equal to x squared minus 4x plus 5. X squared minus 6x plus 9 is equal to 0. X minus 3 all squared is equal to 0. So we have repeated roots, and the solution is x equals 3. We can now substitute this back into equation 2. So substitute x equals 3 into 2, and we'll get y equals 2. So the coordinates of the point of intersection is going to be 3, 2. So on the graph, what this represents is where the straight line touches the parabola at the point 3, 2.